Okay. Was that on with the question?
No, it was Harry.
Harry, go ahead, Carrie.
It was the precipitation lab. I have a question about for the assignment for question 4 and question 6.
Now let's take a look at question 4 here. So I'm opening up the home page. And precipitation reactions lab assignment is what we're looking at. And you're looking at question 4. For the compounds that dissolve, show a figure of the change on the ionic level. Is that the one we're talking about?
Yeah, that one.
Okay, so what I'm going to do here is I'm going to close this, and I'm going to open up the lab notebook part. Now, in the lab notebook part, do you see what I've, you can't see it, never mind. So this is what I'm looking at from the lab notebook part. And this first part talks about sodium chloride dissolving and how we can write the equation 2 ways. Do you see that below? NaCl solid turns into Na aqueous plus Cl aqueous.
Yeah.
Or we can write NaCl solid turns into NaCl aqueous as one formula. Now, if you take a look at what I've drawn above, do you see how the left is supposed to look like a crystal lattice of sodium chloride?
I see that.
Okay, and on the right, do you see the little squiggly line at the top? That's supposed to be water.
Yep.
So what has happened to the ions? Are they well ordered and stacked anymore?
No, they're not.
So they're what? Surrounded by water, right?
Yeah.
This is the type of drawing I'm asking you to do for one of the compounds that dissolve.
Oh, okay.
So I'm asking you to kind of do this, but with a different compound. So you're going to have to draw a nice 3D structure. You don't have to draw 3 lines of it. If you draw 2 lines of it, that's fine. Are you with me?
Yeah, I'm with you.
Excellent. Okay, so I'm going to go ahead and close this window, and I'm going to open up the lab assignment and go to number 6, okay? So number 6, for one of the precipitation reactions, draw a figure showing what happens on the ionic level. Okay, so I'm going to close this, and guess where I'm going to go?
To the lab notebook.
Lab notebook. So with these particular instructions, I tried to give you some guidance in the lab notebook. Now, if you take a look here, this shows you sodium chloride dissolved, and this shows you sodium nitrate dissolved. When you mix the two together, none of the ions have met except for these 2 at the bottom. When they meet, they stick together. And what I've drawn here is all of these ions, all of the silver ions and chloride ions sticking together into a lattice. So this middle drawing is not necessary for what I'm asking for. You should draw 2 containers, one for one test tube, one for the other test tube, and then you should draw what you see afterwards when you combine the 2. And what I've done here is, since I put these 2 test tubes together, I decided I'd better make this one a really tall test tube to contain all that liquid. So this middle thing you don't need to draw. This just shows what is in progress till you reach the end. Are you with me there?
Yeah.
And that's all I'm looking for.
Oh, all right. And then I just have a clarifying question with the lab itself, so with the lab notebook.
Yeah.
With mixing them together, do you want us, because it says, you says for the precipitation part, mix pairs together. Do you want us to put 2 substances into one of the little beakers and then put water in it, mix it, or?
No, you already have 3 solutions that have dissolved, right?
Right.
So I'm going to do a different share here now. So the question is, what do we mix together? So you take 5 substances
Right.
and you try to dissolve them. Now, 2 of them end up being cloudy. And 3 of them ended up being clear and colorless. That's what should have happened. Okay? And if you didn't get 3 being clear and colorless, you probably added not enough water. Are you with me?
Yeah.
Okay, so let's call this A, let's call this B, and let's call this C. So what you're supposed to do is take a little bit of A and a little bit of B and mix them together. So I'm going to call this AB. You're supposed to take a little bit of A and mix it with C, and a little bit of B and mix it with C, and see what happens. So you only have 5 test tubes, so you got to kind of figure this out, right?
Oh,
And
okay.
what makes sense is to do something like this. Maybe you take your A, and with one of these test tubes, which you've cleaned out, you put A into 2 test tubes, right? And with your B, with one of these test tubes cleaned out, oops, you put it into 2 test tubes. And so now you can mix these 2, and that's your AB. You can take a little bit of C and put it in here, and a little bit of C and put it in here, and you don't have to do too much work there.
Right.
Does that make sense?
Yeah, no, that makes sense.
So you don't need to create more dishes for yourself. You just need to think about how you can use what you have.
Okay. All right.
All right, very good. Now I'm going to go back to my, well, I'm going to keep the share here and ask, does anyone else have any questions? Okay, since you don't have any questions, what we're going to do then is turn this into doing problems at the end of the chapter. So I have some prepared for us. I don't know if I have too many prepared or too few. We'll see. But where we had left off was we had left off on determining what things will dissolve and what things won't dissolve based on the formula. So in other words, we were doing some precipitation type stuff and solubility type stuff. So now we're going to take this to the next level here. We're going to take a look at those solubility guidelines and figure out what's going on with a precipitation reaction. So in a precipitation reaction, 2 aqueous solutions are mixed and you get a solid, an ionic solid. And these 2 aqueous solutions are ionic aqueous solutions. So ionic means it's an ionic compound. Aqueous means it's dissolved in water. And solution means that it's evenly distributed. Okay, so balance the equation for the following precipitation reaction, then write the net ionic equation. So because I know it's a precipitation reaction, I know right away that this is aqueous and this is aqueous because the precipitation reaction involves 2 aqueous solutions that mix together. And as far as these go, I want to figure out which one of these is the solid and which one is not the solid. In our solubility rules, we have the always soluble. Now, this is not the complete rule here. These are the ones that I memorized because they're the ones you run into most often. Always soluble, potassium ion, lithium ion, sodium ion, nitrate ion, acetate ion. So these are the ones that I memorized because they're the ones you run into most often. So that means if the compound has one of these ions in it, it's soluble. Let's take a look at this compound. Does this compound have any of these in it? And the answer is no. Okay, so that's not soluble. Not soluble means it will be the solid in solution. It will be the white stuff that precipitates. Does this have an always soluble ion in it? And the answer is you bet. It's got the nitrate, so this will be aqueous. Now, we're supposed to balance this, so let's go ahead and do that. When you're balancing these precipitation reactions, you balance not only by atoms, but also by ions. Really, you balance by ions. Here we have a nickel ion, one of them. Here we have a nickel ion, one of them. Here we have 2 nitrate ions, and here we have 1 nitrate ion. So if I put a 2 here, I now have 2 nitrate ions. Here I have 2 sodium ions. Here I have 2 sodium ions, 1 carbonate and 1 carbonate, and this is balanced. Now, if you're okay with this explanation, give me a thumbs up and I'll move on. Excellent. Now remember, if you don't want to take notes on these things, you can always take a picture before I start writing on this. And I apologize for my hand being in the way, but I am left-handed. And I'm too old to learn how to write right-handed. Okay, predict the products of each precipitation reaction, balance the equation, and then write the net ionic equation. So let me show you a way to figure out what the products are going to be. Figure out, first of all, what all the ions are. I know each of these is ionic because it has a metal and nonmetal. And I know that the first thing that shows up is going to be the cation, and the second thing that shows up is going to be the anion. In this case, I know the nitrate ion has a -1 charge, and because there's 2 of them, I know that the lead has to be a +2 charge, so that all the charges, when you add them up together, +2, -1, -1, 2 of them, they add up to 0. So these are the ions in lead-2 nitrate. And potassium is always a +1 ion because it's in group 1A. Bromine is always a -1 ion in ionic compounds because it's in group 7A. So plus and minus. Now what you do is there's 2 ways to do this. One way is look at all the possible ionic compounds that could form. For instance, you could have lead-2 nitrate. You could have lead bromide. You could have potassium nitrate, or you could have potassium bromide. And you look at each of these and you ask yourself, according to the solubility rules, which ones are soluble? And the answer is, this one is soluble, so it would be aqueous. This one is soluble, so it would be aqueous. This one is soluble, and it would be aqueous. Now, why is each of these soluble? This one, because it has the nitrate. This one, because it has the potassium and the nitrate. This one, because it has potassium and the bromide. Most bromides are soluble. Now, there are some exceptions to the bromides being soluble. One of those is if it's combined with the lead. So here it's being combined with the lead, so this would be the solid. So that's one way to figure out what the solid would be. The other way to do it is this way. Look at all of these ions. If there are any always soluble ions, take them out. And whatever remains must be the solid. So the solid must be lead-2 combining with bromide, which means lead Br2 to get a neutral formula, since this is a +2 and this is a -1. So we put a solid here, and then we write the remaining ions, which is the potassium and the nitrate. And now we balance. Notice when I write these formulas, I don't care how many ions are present. All I care about is writing the formula of an ionic compound. Okay, so 1 lead, and actually I should say 1 lead-2, 1 lead-2. 2 nitrates, 1 nitrate, so I put a 2 here. 1 potassium, 2 potassium, so I put a 2 here. 2 bromides, 2 bromides, it's balanced. All right, so for this one down here, we can kind of list the ions again. We know that's a +2 because it's in group 2A. We know this is a -1 because you're supposed to have memorized it. We know that's a +1, and we know that's a -1. Any of these ions always soluble? And the answer is these two. So what does the solid have to be? Calcium and fluoride. And you do the switch and simplify. So what's the other compound? We combine these two ions. And that's aqueous. Now these two ions, I have the nitrate first and the potassium second. Why is it that I write the formula with the potassium first and the nitrate second, even though over here they're reversed? And the answer is when you write the formula of an ionic compound, you always write it so that the cation is first. Okay, now to balance this, what should I do here? It looks like I have one calcium, two nitrates, one nitrate. So I put a 2 there. Two potassiums here, one potassium, so I put a 2 here. Two fluorines, we're good to go. Okay, so now this one's a little more complicated. And it's not because of the calcium nitrate. We've already seen that. We may not be familiar with this ion, but we are familiar with sodium ions. So there's 2 of these sodium ions. What is the C2O4? It is an ion. Now, if there's 2 sodiums and 1 of these, what does the charge on this have to be? -2. And in fact, it's called the oxalate ion. All right, so I'm going to stop here for a moment. I'm going to pause the recording. Okay, so we're in the middle of another problem. We can take a look at the resolution of the previous problem after we finish this one. So what we're doing right now, again, is we're showing what happens with the Arrhenius definition. So what does this formula look like if it's got 1 less hydrogen? HPO4. That's 1 less hydrogen. What does the charge on this have to be, considering that this side has a -1 charge and this whole side should have a -1 charge? What should the charge on that be? And the answer is -2. So we're balancing it not only by atoms, but by charge. This is an acid. Okay, folks, you're on the hook now. What are the 2 products? When you're ready, give me a thumbs up. Okay, we've got 1. We've got 2. Do we have liftoff? We have 3. Excellent. So would you like to see what I would write? Here we go. H plus PO4 -3. Now, this is not the answer that the book is looking for. It's looking for this. H3PO4 aqueous reacts with H2O liquid, and it makes H3O plus. This is called the hydronium ion. It is a polyatomic ion. It's not one that we asked you to memorize because you don't find it in ionic compounds. You only find it in water. Now, how do I figure out what this one is going to be? It's this minus an H plus. So H2PO4 minus 1. And I can still figure out the charge on this by knowing that this side, which is 0, has to equal this side to be 0. So plus 1 minus 1 is 0. This is an acid. It reacts with H2O. So guess what I want you guys to do? I want you to get these two answers, then do the next one also, and give me a thumbs up when you're ready. Okay, so we're going to write H3O plus aqueous plus HPO4 aqueous. And since this side adds up to -1, I want this side to add up to -1. So I'm going to put -2 there. Then we're going to start with this. This is an acid. -2. It's going to react with water. When it loses a hydrogen, it becomes PO4. And this side, which adds up to -2, needs to equal this side to add up to -2. Since this is a +1, this is a -3. How'd y'all do? Okay? No? Give me a thumbs up or a thumbs down on how you did. Good. Now, let's go back to that problem where I paused and I made you figure out the answer. So that was this problem right here. And what we had done here is we figured out the ions. Since these two are always soluble, we combine these two to make the solid. We took the other two ions, which are called spectator ions because they don't really react, and they made the aqueous ionic compound here. And then to balance it, because we had 2 nitrates here and 1 here, we put a 2 there. We had 2 sodiums here, 2 sodiums here, 1 oxalate, and this is balanced. The other thing that we missed was this. We didn't record this. Write a balanced equation for the ionization of perchloric acid in water. So this is a perchloric acid formula. And this is the Arrhenius answer. You just take the acid, take an H plus off of it, and whatever remains minus the H plus, that's what you write as the other product. This doesn't really happen in water. There aren't really any hydrogen ions in water. What really happens is that the acid reacts with water, and the acid donates a proton, so that means it loses a hydrogen. And when it loses a hydrogen, it becomes this. And because it loses an H plus, not only does it lose a hydrogen, but it loses a charge. So 0 goes to -1. This is a base, and a Bronsted-Lowry base is a proton acceptor. So this accepts the proton, H plus. So H2 goes to H3, and neutral goes to +1. These two are called a Bronsted-Lowry acid-base pair. They differ by 1 hydrogen with a plus charge. And these two are a Bronsted-Lowry acid-base pair. They differ by 1 hydrogen with a plus charge. Okay, so that's what we missed. And now we're going to go back to this. And if this is a Bronsted-Lowry acid, what does that make H2O? A Bronsted-Lowry base. Now, what about the other side of this reaction? Which is which? Well, let's just compare. Do you see how these two differ by one hydrogen? This one is a Bronsted-Lowry acid, and the reason I know that is that when you find the conjugate pair, the acid has more hydrogen. The acid has more hydrogen. Okay, look at these two. Which one has more hydrogen, left or right? And the answer is the left. So that makes the right one a Bronsted-Lowry base. So I want you folks, for the next reaction, to name the first two things and the last two things as either Bronsted-Lowry acids or bases. When you're done, give me a thumbs up. If you're having a little difficulty, give me a thumbs down. If you're dead or passed out, give me a thumbs down. Really, on? You're passed out? Okay, judging by how slow you're going, I think you're having difficulty. Let's look at this top one again. And let me give you some hints on how to figure this out. Okay, tell me if you're ready. Give me a thumbs up if you're ready. Okay, first thing you want to do is get the pairs. They differ by H plus. So look at this guy here and this guy here. Do these differ by only one hydrogen? And my answer is no, they don't differ by hydrogens. And this one's got a phosphorus and this one doesn't. They're not a pair. Oops, this should be a 2 here, like above. Let's look at these two. Do these differ by one hydrogen and a plus charge? And the answer is yeah, 3 hydrogens, 2 hydrogens, 1 phosphorus, 1 phosphorus, 4 oxygens, 4 oxygens, 0 charge, -1. It differs by an H plus. So that makes this a pair. So now let's take a look at the water and compare it to this guy here. Are these a pair? And the answer is no, they don't differ by any hydrogens, and they differ by a phosphorus also, and the number of oxygens is different. The charge is different by 1, so that's good, but there's too many things that are wrong here that make these two not a pair. How about these two? Are they a pair? Absolutely. They differ by 1 hydrogen and a plus charge. I'm not going to put conjugate in here because it's just too crowded. Now that we've identified the pairs, so get the pairs by, they differ by 1 hydrogen, right? Next, you ID the Bronsted-Lowry acid and the Bronsted-Lowry base of each pair. The Bronsted-Lowry acid has more hydrogen. So here's a pair. Which of these two is the Bronsted-Lowry acid, left or right? If you think it's left, go slower. If you think it's right, put go faster. We're asking which is the acid. Go slower for left, go faster for right. You guys aren't used to picking go slower and go faster. Correct. This is the Bronsted-Lowry acid, and this is the Bronsted-Lowry base. Now, let's look at these two. Which one is the Bronsted-Lowry acid? If you think it's the left one, put go slower. If you think it's the right one, put go faster. And that is correct. So this is how you do it. Get the pairs and then identify the acid of each pair and the base of each pair, and you're done. So let's take a look at this second reaction here. And what I'm going to do here is I'm going to get a fresh piece of paper and write it on here. And I want you to identify the Bronsted-Lowry acid and the Bronsted-Lowry base on both sides of this reaction. When you're done, give me a thumbs up. Am I recording? I wonder. Yep, I'm recording. Identify pairs. And then for each pair, one's an acid, one's a base. The acid has more hydrogens. And give me a thumbs up when you're done. Okay, so let's see how you did. This is a pair because they differ by one hydrogen. And this is the acid because it has more hydrogens. This is a pair because they differ by one hydrogen and a charge of one. This is the base because it has fewer hydrogens. Do you see how I tricked you up there? Instead of going for the acid first, I went for the base. And I said, this is the base because it has fewer hydrogens. Just trying to keep you on your toes and making you think about it from all different angles. So there you go. One more try. I want you to identify the Bronsted-Lowry acids and Bronsted-Lowry bases in this reaction. When you are done, give me a thumbs up. Wow, that was fast. Okay, so let's check your answers. This is a pair. This is the Bronsted-Lowry acid because it has more hydrogens. And this is the Bronsted-Lowry base. And this is a pair. And this is the Bronsted-Lowry acid. And this is the Bronsted-Lowry base. This is the acid because it has more hydrogens. Do you see how I switched these two on you? Did anyone fall for my trap? Or did you all get it? Did you get it right? Give me a thumbs up if you did. You didn't fall for my trap. Excellent. So that means that you learned what you needed to do. Good job. Okay. So next, we have this question about write a balanced reaction of sulfur trioxide gas with water. This has to do with oxides, metal oxides and non-metal oxides. Now, when you take a metal oxide and mix it with water, you get a base. When you take a metal oxide and mix it with water, you get an acid. And this sulfur trioxide gas is a component that you get when you burn coal, because coal is largely carbon, but it does have a lot of other things in it like sulfur and nitrogen and so forth. So when you burn coal, what happens with the sulfur is a lot of it gets oxidized into sulfur trioxide. So sulfur trioxide is a gas. You burn the coal, it goes into the atmosphere. And then rain hits the sulfur trioxide and it dissolves it and it reacts. So your non-metal sulfur trioxide, non-metal oxide, is going to mix with water to get an acid. Now, let me give you an example of a different one other than sulfur trioxide. Have you guys ever heard of CO2 gas as a component of making or burning coal? Right? Let's see what happens when you mix this with water. Well, what happens here is you get 2 hydrogens, 1 carbon, and 3 oxygens. This is called carbonic acid. And it is a component in something called acid rain. Has anyone ever heard of acid rain? This is not a sci-fi thing. This is sci thing. So back in the 70s, there was a term coined acid rain for what was happening to a lot of the different monuments in the world. So a lot of statues are made out of something called calcium carbonate or limestone. Calcium carbonate reacts with acid. So here's acid from acid rain. And what happens is you get CO2, H2O, and you get, the other thing that you get here is, what do we get? I have to think about this. I believe you get calcium hydride. I could be wrong on that. At any rate, what happens is your statue dissolves. So you can take a look at on Google about acid rain, and they'll show you pictures of like statues that are outdoors, and they'll show you like a before picture, and then after the Industrial Revolution, they'll show you an after picture, and these things have dissolved. So carbonic acid can do this, but the problem really is these other gases here, like sulfur trioxide. So this isn't really a big deal because this is a weak acid. So what is the formula for sulfur trioxide? SO3 reacts with H2O. What are you going to get? See if you can figure it out. If you think you get the answer, give me a thumbs up. When you're trying to think of the answer, you should think, well, I know I'm going to get an acid, so the formula begins with hydrogen. The next thing you should say is, well, I've got 2 hydrogens here, so in my formula, there should be what? 2 hydrogens. How many sulfurs? 1. How many oxygens? 4. This is called sulfuric acid, which is a strong acid. Okay, so you don't hear about acid rain anymore. Why is that? Well, they have a number of different ways of removing the sulfur trioxide gas from burned carbon. They don't really care about the CO2. This really isn't a big deal. But when you have a gas that makes a strong acid, you want to take it out. So basically, if you can take all of your gas and run it through water, you can make sulfuric acid right at the plant and siphon that away and maybe even sell it. So we don't have a problem with acid rain anymore because scientists discovered the problem, thought about the solution, and boom, you got the answer. Better living through science. This is why you should listen to those scientists who, belong to a large group. They have peer review. And usually when you have the majority of scientists agreeing on one thing, it's probably a good bet to go with that. Have there ever been issues where the majority of scientists have been wrong? Yeah. But if you went to Vegas and you bet on the scientists being wrong as a whole, you would lose your money so fast, faster than if you go to Vegas and lose your money right now. You want to bet on when the scientists collaborate, come to a conclusion, and support that conclusion. There's always going to be someone on the outside saying, no, 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 that's not the way it is. The earth is flat. But it's not. Okay, moving on. Complete and balance equations for the following acid-base reactions. Name the products and name the reactants. Now, to balance an acid-base reaction, we don't really follow the Arrhenius definition or the Bronsted-Lowry definition per se. Here's what you do. An acid plus a base will react and give you water and a salt. Salt simply means an ionic compound from an acid-base reaction. Now, the key to balancing acid-base reactions is this. You need one H plus to react with one hydroxide and you get one water. You need one of each and you get one water. So let me show you how to figure out how many hydrogens you have in your acid. Usually it's going to be right at the front of the formula. This has 3 hydrogens. Now, how many hydroxides does it have? Usually you can tell from the formula. No subscripts, 1, subscript 2. Okay, now, is this a ratio we want? Remember, we want a ratio of 1 to 1, and we get 1. But this ratio also means we could go 2, 2, 2, 3, 3, 3, 4, 4, 4, 5, 5, 5. The point is, you need to have the exact same number of hydrogens and hydroxides, and you'll get that many waters. So when I have 3 hydrogens here and 1 hydroxide, that's not a match. So what I want to do is I want to get 3 hydroxides, and to balance equations, what are we allowed to do? And the answer is change the coefficient. So if I put 3 here, that means I will have 3 hydroxides. So how many waters will we get if we have 3 protons and now 3 hydroxides? And the answer is 3 waters. Now to finish this off, we just look at what's remaining. We have 3 potassiums remaining. We have a phosphate remaining. And we just put those together. K3PO4. Now, will this be aqueous or will it be a solid? According to our solubility rules, anything with potassium in it is soluble, so this would be aqueous. And that's how you balance an acid-base reaction. First, you need to ID the acid, ID the base. Second, you have to count protons, hydroxides, and then 3, you have to change coefficients so that the number of protons equals the number of hydroxides, and then 4, the number of protons equals the number of hydroxides equals the number of H2O, and then 5, the remaining ions make the salt. So that's how you balance an acid base. If you're okay with that, give me a thumbs up. Okay, I want you to balance this one. Now notice this says diprotic. Diprotic means that it has 2 hydrogens. So when you're done balancing this one, give me a thumbs up and we'll go from there. So the first thing you're going to think about, 2 hydrogens and 2 hydroxides means how many waters? How many waters? Two water. So if we've used those 2 guys left up, we have this guy left over. And if we've used these 2 guys, you've got this guy left over. So put them together. Now, you have to look at your solubility rules. Soluble or insoluble. And the deal is you're going to say, well, since it is not part of the soluble rules, it's insoluble. Now, this is by no ways and means a precipitation reaction. It's an acid-base reaction because you have an acid and a base. All right. So let's move on. Write a balanced equation for the reaction of aluminum hydroxide with sulfuric acid. Now, aluminum hydroxide, we know has aluminum in it, and we know it has hydroxide in it. So what's the formula for aluminum hydroxide? AlOH3. 1 aluminum because that's a 1. 3 hydroxides because that's a 3. What's the formula for sulfuric acid? Well, that one you need to memorize, H2SO4. So here are the 2 things that you are mixing together. Don't worry about the states. I want you to write out a balanced acid-base reaction. And when you're done, give me a thumbs up. Or if you get stuck, give me a thumbs down. How you doing, On? Okay. So first you identify the acid and the base. Then you identify how many hydrogens and how many hydroxides. 2 hydrogens, 3 hydroxides. And you can see that this is a bit tricky because with 2 and 3, how do you match that up? And the answer is you want to go for 6. So you need 6 hydrogens and 6 hydroxides. And when I chose 6 because 2 times 3 is 6. So how do I get 6 hydroxides here? I put a 2 in front of there. How do I get 6 hydrogens here? I put a 3 there. Now, if I have 6 hydroxides and 6 OHs, how many water do you get? 6. Now, what's remaining are 2 aluminums and 3 sulfates. And all you do is you put them together. That's how you write 2 aluminums. How do we write 3 sulfates? What do you think of this? Does that look good for 3 sulfates? Does that look good?
No, you need a, oh, well, I guess I'm talking. You need the parentheses around it.
That's correct. And this is your balanced acid-base reaction. Fair enough? Okay. Okay. Write an equation that describes the equilibrium that exists when a weak acid dissolves in water. Identify each of the 4 species as either Bronsted-Lowry acid, Bronsted-Lowry bases, and then does equilibrium favor products or reactants? We've done this before. We did this for phosphoric acid. That was a weak acid. So we're going to do the same thing for this. So what is one of the products going to be, because we're already used to it? H3O plus, right? So over here, we need to write this with 1 less hydrogen. And a great question is, one of these or one of these? Our first thought is to be kind of generous and say, well, since there's only one of these, let's let it stick around and take one of those. Well, it turns out that anytime you have a molecule with this in it, this guy here is acidic. So that means we want to take this guy away. So we take away a hydrogen and we take away a charge. If this charge is 0, what is the new charge here? -1. And they say this is a weak acid, so that means we do this. And now I want you to identify Bronsted-Lowry acids and Bronsted-Lowry bases. When you're done, give me a thumbs up. Do you remember how we started this one? First you get the pairs. Okay, so I'm hoping that you found this was a Bronsted-Lowry acid. And over here, this is the Bronsted-Lowry base because that's a pair. This is a Bronsted-Lowry base, and this is a Bronsted-Lowry acid because that's a pair. Now, the question here is, does the equilibrium favor the products or the reactants? And we can answer this. Strong acids, you favor the products. Weak acid, you favor the reactants. Okay, so what is our answer to this one? Product or reactant favored? If you think it's reactant favored, go slower because that points to the reactant side. If you think it's product favored, pick go faster because that picks the product side. Go slower is correct. It's a weak acid. How do we know? They tell us. Now, there's something else I do want to tell you. Whenever you see this, that's a weak acid. Whenever you see that, that's a weak acid. You might see it another way though. So this is a weak acid. Here's another way they write it. CO2H instead of COOH. Okay. Write two chemical reactions, one in which H2PO4 is a Bronsted acid with CO2, CO3 2-, and a second where this is a Bronsted base. Okay, so here, H2PO4- plus CO3 2-, they want this to be an acid and they want this to be a base. So how do we write the reaction? So I want to draw the pair. So what's the Bronsted-Lowry acid of this guy? And the answer is, I'm going to add a hydrogen to it. But I'm not really adding a hydrogen, I'm adding an H+. So if I add an H+ to this, the charge becomes -1 because -2 and +1 is -1. So remember, they differ by 1 hydrogen. The acid has more hydrogen. So here, I want to draw the Bronsted-Lowry base of this. Am I going to add a hydrogen or take one away? And the answer is, I'm going to take one away. Now, as far as the charge goes, I'm taking away an H+, which means the charge becomes more negative. So that's a -2. Another way to figure it out is to say, well, this side adds up to -3. This side has to add up to -3 also. And since I figured out this is a -1, that has to be a -2, so it adds up to -3. So we've shown a reaction where this dihydrogen phosphate is a Bronsted-Lowry acid, and it reacts with CO3 2-, the carbonate ion, a Bronsted-Lowry base, to make this pair. So now your job is to take HPO4 -2 and react it with CH3CO2H, and they want this to be a Bronsted-Lowry base, so this is a Bronsted-Lowry acid. Write the products and label them. When you're done, give me a thumbs up. Personally, I like to start with the base because I just add H+ to it. All right, let's check. So I'm going to add an H+ to this and get H2PO4. -2 and a +1 changes that to -1. And here, for the acid, I need to take away a hydrogen. Do I take away this one or one of these three? And the answer is I take that one away. Now, if I want to figure out the charge on this, I can do it two ways. I'm going to do it this way. This is -2. This is 0. This side adds up to -2. This is -1, and this side has to add up to -2. So this must be -1, and we're done. Okay? We're going to save this one for next time because it's kind of the next section. We'll finish off most of the rest of the chapter as far as example problems go on Wednesday. I do have a question for you folks. Have you been watching? Go ahead and unmute yourselves because I want to hear what you have to say. Have you looked at the new videos for the chapter? There's 9 of them, I believe, or there's 11 of them. Have you looked at any of them?
I don't think I've gotten around to it yet, but I think I am gonna watch them tomorrow.
Okay. The deal with the videos, there are 9 of them, and in the past, the videos have been about an hour apiece.
Right.
I've changed that. Now the videos are about anywhere from 10 minutes to 20 minutes apiece. So that's why there's 11 of them. 11 of them at an average of 20 minutes makes them about 200 minutes total, or 3 hours. So there's about 3 hours of lecture for the chapter. You might want to take a look at those videos because they're shorter and you can do them in little chunks. All right?
Yep.
These videos that we do for these study sessions where I'm doing problems, they will end up being an hour long because we talk for an hour. In addition, for those little short chunk lecture videos, what I do is I'm copying problems out of the back of the book and incorporating them into the videos and showing you how I do them, much as I'm doing here with these problems. These problems are different than the ones I do in the lectures. The problems I'm no longer doing in lecture are the example problems in the book. You should do the example problems in the book. And since the problems are explained in the book, there's no need for me to explain it to you. So I'm going to try that for this chapter, the next chapter, and the following chapter. And that's about it. I put an announcement out that all the lectures are there. I'm going to post a Q&A discussion session for you guys to contribute to in a bit today. And what's the other thing? Oh, your quiz on this next module is going to be Friday. All right. So thanks for listening. Turn your mics on and say goodbye.
Bye, everyone.
All right. We'll see you Wednesday, I hope.
Yep.
Bye-bye.
Bye.